So originally, our rover was built using these controllers for servos and motors called fidgets that our team unfortunately didn't like. A lot of the issues we ran into fidgets was through our software framework, ROS, or the Robot Operating System. A lot of the packages that were already in ROS had mismatched versions, and the ROS package for fidgets was built on top of a package for another robot that we didn't want to incorporate. So our team in the end decided to replace fidgets with Arduinos instead, because we had a lot of Arduinos on hand and there's a great community and it's open source, so it was really easy to develop, at least for the purpose of this project.
So the chassis itself is really just a container for the onboard electronics. The suspension mounted around it is a rather unique design, kind of known as a shrimp design. The biggest feature of this is a big front fork for a front wheel that can kind of articulate over things and pull the rover over objects much larger than its relative size. The 4-bar linkages along the side are passive, and they allow for the wheels to adapt to a changing terrain independently on each side. All of the wheels are actually powered, so we have 7 powered wheels on 5 channels. And so we'll be able to climb over rocks that potentially other teams just can't. We'll be able to climb over rocks that are larger than the rover potentially, and all of this will be rigorously tested in the following months. So the new wheels were designed more or less because the old wheels fell off. The hubs were flat, and the 3D printing was done with a low percentage of infill, which means they weren't solid. And so as the rover sat on the wheel would actually bend, and it would actually break the wheel. So we redesigned the whole thing to have a flexed hub, and that would be much stiffer and much more resistant to any kind of bending. So the spokes are curved inward to reduce the moment arm of a force being applied to the very edge of the wheel, and the barrel shape helps gain traction when we're on angles on uneven terrain.
So ROS is really easy to use and is used by a lot of robotics company. There's a lot of documentation for it, as well as different robots that have been using it in the past. So what's nice about ROS is that it provides a node-like framework that lets us control the different aspects of our rover through a centralized system. It lets us control the motors, the servos, and the camera. So right now we are running a server motherboard on our rover for processing. It includes a built-in quad-core processor as well as 16 gigabytes of RAM. So a lot of processing power we have on board so that we could process the data directly instead of having to send it over to mission control, process it there, and then send it back.
So currently, for testing purposes, we're operating off a 4-input, 4-output motor driver. It's serving its purpose for testing, but will not be efficient for competition. The motor driver that we are designing is going to be 5-input, 5-output, and we'll be using the same microcontroller on board as the microcontroller on an Arduino. And this will also allow us to use some pre-built software within ROS to communicate between the Arduino and main operating system. By using a 5-input, 5-output channel motor driver, each motor will be ran off its own circuit. So if one part of the circuit actually fails, all 7 of our motors won't fail, which will allow for redundancy within the competition in case of failure.
So the original batteries, we started with 6 amp hour batteries, and they were acidic batteries. So they were really heavy, and each of them was 6 amp hours, so it didn't really have enough power to power our rover for a whole hour as the competition requires. Our new batteries, they're lithium ion, and they're 20 amp hours. Our power budget right now is a little bit over budget because we're just assuming all the elements of the rover are running constantly for a whole hour. Using the codes with power efficiency that should at least give us an hour and a half running continuously without the needing of the recharge.
So we'll be communicating with it over a 3 and 4G network modem, which you can see in the shot behind me. It's a Cradlepoint IBR 650, which we were inspired to get out of some of the promo video from last year's competition. As a couple teams were talking about communication issues and moving to the Cradlepoint type routers to solve those. So right now we're running it over a Wi-Fi card that's built into the motherboard on the system, and it works very well. All we need to do is replace that card with this modem on an Ethernet port, and we'll be rolling.
So our sample acquisition strategy is going to start at the arm. It's a pre-purchased 4 degree of freedom arm, and at the end of it is going to be our gripper. Originally, our gripper was similar to a backhoe arm with a thin plexiglass piece at the end of it. And the idea is if we put a camera right at the end of the arm along with the gripper, as we're picking up rocks, we'll be able to see through that plexiglass piece and pick the rocks up. The issue with that is that we eliminated one of our degrees of freedom. So our new gripper design, we originally got the idea from Cornell University, and the idea is to use a balloon, coffee grounds, and a vacuum. So when we find a rock, what we're going to do is we're going to take our gripper, we're going to aim it just above it and stick it right on top of it. The coffee grounds inside the balloon are going to form around any object that we want, and then we're going to send a signal to our pump. It's a small 12-volt pump, and it's going to apply a vacuum to the balloon. And once we apply that vacuum, it's going to take those coffee grounds, and instead of being kind of in a liquid form, are going to act as a solid. And that solid's going to conform around the object and allow us to pick it up. What that enables us to do is not only pick up rocks, but any other unique shapes as well, including any surprises that Rascal has for us. So far, our gripper has done phenomenally well. It has been able to accomplish every goal that we've set for it, including be able to pick up many rocks one after another in succession, which isn't even something we expect to do in competition. The gripper itself has been very resilient. We've even made fun of our project leader. He's doubted the ability of our balloon itself. But just in case, we have many plans for a second gripper. So our second gripper is going to be much different than the granular gripper. It's going to be more similar to a claw design, and we think that that's going to add a level of redundancy just in case we run into some problems that we haven't been able to test or things that our gripper can't do. But up until that point, we're going to continue testing on a granular gripper to ensure that it's just not up to snuff.